Good afternoon, everybody, and welcome. Last week, we announced that Dr. Ryan Lefevre would lecture us today, but for reasons beyond our control, he couldn't be here with us. Professor Elliott was kind enough to reschedule the continuation of last week's seminar for today. Since he needs no introduction, I'm just going to thank Professor Elliott for making himself available to us and ask him to start. Thank you so much, Professor.
Okay, thank you. So let's see, I'll share my screen. Well, okay, let's just share everything. Yeah, that's what I meant. So, okay, thanks. It's unfortunate to have this opportunity, but I think maybe it's good for me in the sense that there'll be less time between last week's lecture and this one. So this is really the topic that I wanted to talk about, and my motivation was that in the seminars that you had last semester, you didn't hear a lot about integral equation theory, and I think that it's an important perspective, and I'll try to get that across through the course of this lecture, which is kind of one application, one specific narrow interpretation of the field, and then at the end, you know, I'll try and mention some other papers that have been out and how you can learn more. And I'm starting my watch so that I can keep track of how far over time I am. Okay, so what I'll do to hopefully cover things as quickly as possible, and still keep you up with understanding everything. I'll first cover some review, some things very similar to like last week. I'll just keep building, and these are things that we talked about last week. These are things that we talked about a couple of lectures ago last semester, where we showed that the higher order perturbation contributions, if you plot them as a ratio, they look a lot like a Gaussian function with its peak near the critical density. And that makes a lot of sense if you think about what fluctuations of fluctuations might look like and the way that a Gaussian works. And so it becomes more and more peaked as you go towards infinite order in some sense. And so we'll try and investigate that perspective to higher order being third order and fourth order in this case. And we want to generalize beyond spheres. And to do that, we want to use an interaction site model, which basically just means we'll have one site for a CH3 and one site for a CH2, and you put two CH3s and three CH2s together and you get pentane, right? So that's an interaction site model. The R here stands for reference interaction site model, which is just the name that Chandler came up with for his theory of an integral equation theory for a collection of spheres attached to form a molecule, right? It's the interaction site model. And the P here stands for the polymer version of that. And essentially what the polymer version does is it ignores the distinction between the CH3s and the CH2s because there's relatively few CH3s. There's very few chain ends if you're talking about a polymer. So let's just neglect that difference, or at least maybe we should average it out. And if you have a lot of CH2s and very few CH3s, then they'll look just like CH2 interactions, right? So that I want to give you a little background on that PRISM theory, and then we'll take a look at what we can learn when we apply this PRISM theory and we make an adaptation for it in the form of perturbation theory. And so CPE stands for a coupling parameter expansion. It's one way of deriving these terms A3 and A4 and A5 and A6 and A7. What you're going to see is that we can recover the asymptotic trends of the perturbation contributions within this PRISM-TPT theory. What am I talking about there? Again, way back, we talked about it last semester. We talked about the perturbation contribution of A1, let's say, divided by the number of carbons, and you make a plot of that versus density for octane. Then you do it again for decane, C20, C50, C80. And you see that when you divide by that number of carbons, the distinction in that curve becomes less and less. I'll show you a graph in the course of the lecture, but you've seen the graph before, so I'm just kind of reminding you of what it looked like. And so it looks like a rainbow, right? And so you've got different colors for different chain lengths. And because you're dividing by the number of carbons, eventually the distinction from one carbon to another is washed out. And you have this polymer limit where it looks like just one curve. And so that's your asymptotic limit. And what we're going to see is that we get the same trend when we use PRISM theory. And that's good. That reassures the things that we derive by doing molecular simulations. And using an accurate A naught, or we could call it Z naught, right? There's this thermodynamic relation between the Helmholtz energy and the compressibility factor. So we can match that A naught by using an empirical tail correction. We talked briefly about fixing that during the Q&A last week, where we said we can put a Yukawa tail for our C at R greater than sigma. Instead of assuming it's 0, we'll assume it's something not quite 0. And we'll characterize that as a Yukawa function. Well, we need to do the same thing to get accurate. And so that's what I mean by accurate thermodynamics in this title. So we're going to match these DMD-TPT results by using this empirical tail. Well, if you think about it, there's a trick to that, because the radial distribution function that comes out of the purely repulsive part also plays a role when you compute the A1 term. We'll see that as part of this review in just a second. And so you have to be self-consistent in the way that you devise that tail so that you're matching the A1 and the A naught term simultaneously. Okay, that's the basic idea. Then we're ready to start taking a look at these higher order contributions. And some interesting things happen when you recognize that a chain molecule might not be completely flexible, right? So instead of being like a tangent sphere chain molecule, the way that we think of in Wertheim's theory, it might be overlapping. And those overlaps cause constraints in the dihedral rotations, so that there's this kind of this irony or counterintuitive result that when you make the bond length shorter, so instead of having tangent spheres, you have the overlapping spheres, like 0.153 nanometers for the bond length. That's your standard carbon-carbon bond length. And 0.36 for your carbon diameter. You see that you've got a lot of overlap. Well, that shortening of the bond length constrains the dihedral angle. It can't rotate as freely now. And we know this from organic chemistry. Well, so shortening the bond length, because it makes the chain stiffer for a longer period of time, it increases the persistence length. Okay, so the persistence length is what you would normally think of as a bond length in the polymer literature. But what actually happens is, because of this dihedral angle constraint, the persistence length becomes longer for the overlapping chains. And so that takes a little getting used to, but it's just a parameter. And you'll see that chain stiffness term has a big impact on these higher order perturbation contributions. Then we can start to look at what does the equation of state look like? What do we learn about this from an engineering perspective as we go to longer and longer chain lengths? So that's the whole talk. If you want to go to sleep now, that's fine. But I wanted to just get across everything that I wanted to say, and then we'll get into the details here. I'll go pretty quickly over some slides. And if you want to look back, you can go through the recording. Here I'm trying to just remind you, way back maybe it was this September, we talked about an artifact-free SAFT equation of state. And these were some of the basic equations that came out of that, recognizing that SAFT is based on a sort of the square-well sphere perspective to get started. I've added one thing here. So this part of this line, this is exactly what I wrote previously. Here I added a little bit to get you to think about, well, if the A1 term is proportional to the G0, just the purely repulsive part of the radial distribution function, then the higher order terms must be related to the delta G part. And so figuring out the details, and especially if we get to mixtures, talking about the composition dependence of these higher order contributions, we need to focus on this delta G contribution. And so you're going to see some graphs of what delta G looks like. And so I wanted to get you thinking about that here early in the lecture. Another thing we talked about was this fundamental definition of the TPT theory and how expanding these exponentials lead to this connection between the classical A1, A2, all of those things, and this ditto means just copy everything in parentheses over again here, and then equating those things at similar powers of beta, and that will give you the perturbation expansion to any order you want, including 4. So wanted to mention that, reiterate that, and then from last week, what we saw is that this radial distribution function for hard spheres with this Perkusiewicz approximation is actually something quite simple. All you have to do, if you can integrate a polynomial from 0 to 1 and throw in a sine function, then you can calculate the Fourier transform of that polynomial, and you put it into this formula, and you get this radial distribution function. So it's not that complicated for hard spheres, and this is exact. This is the analytical solution that Wertheim worked out in 1963. So it's hard, but it's not that hard, right? So then what if we could do the same thing for polymer? That's what we need to talk about now. Now, I wanted to also mention just briefly how we can plot this ratio of A4 over A3 for square well spheres, or A3 over A2. It's not as good, but that's partially because of the weird behavior of A2 at high densities. We see these shoulders out here, and so that's what's causing the thing to go a little strange. What I'm showing here is if we had just a 2-step potential, with the first step was 100%, and the second step was 25%, these shoulders would go away. That's kind of counterintuitive, right? Because this one stops at, the well stops at 1.5. And this one, the well stops at 2.0. So you would think as we just add that second well from 0 to 100%, that we're evolving from the 1.5 to this 2.0. But it doesn't do that. It goes down like this. And so it's that 2-step behavior that's causing the shoulder to go away. Or another way to think of it is this shoulder is caused by that square well. It's an artificial behavior. And we've also made this plot for trapped chains going from methane to butane to dodecane. And you see it gets more scattered. It's harder to get good statistics. But you could rationalize that a Gaussian goes through that curve. And keep in mind that this intercept is given to you by the ratio of the virial coefficients, the perturbative second virial coefficient. And so it's not hard to get a second virial coefficient and to figure out what those intercept values are. We know what the density is, it's near the critical density. And so all we need then is one parameter to characterize essentially the dispersion of this Gaussian, and we've got the entire curve for every higher order perturbation contribution. And then we can come up with different strategies for summing those. And in the 2015 paper, we show that you can get an exact sum to infinite order for square well spheres. And as you would expect, going to higher order helps to flatten the curve. And we can get to within about 0.99 of the critical temperature this way instead of 0.9, which is what the usual theories do. And here I wanted to show you some recent results, not mine, that this should be coming out very soon in the Journal of Molecular Physics. So Sastry and Gilviegas and Benavides, they've been working on this idea for a while that you can look at the fluctuations in just the energy and then extract the higher order terms from that. And so these are approximate, but if you just use their theory as is, you just get these dotted lines, which has the wrong low density limit. But you can fix that because you know through the second virial coefficient what that intercept must be. And so they kind of take their theory up to a point and then they just say, oh, well, connect it down here. And so it's okay. What's interesting about it is if you follow this trend, what we see is that this ratio for A4 is larger than A3, A5 is larger than A4, 6 larger than A5, 7 larger than A. This looks like this series is not converging until we get to A8. So finally, with A8 divided by A7, we see that this ratio, which has to pass the ratio test to converge, we know that from basic sophomore calculus, right? Maybe freshman. Then finally, we have to go to 8th order to see this thing start to converge. So it's converging before, you know, it's, if you think about what your temperature is, the critical temperature and all of that, it's converging, but just barely until you get out to A8. And what we're going to be using here is this couple parameter expansion, where in the first paper, Ramana looked at out to 7th order. So using integral equation theory, you can also achieve higher order expansions. What it looks like to me, though, is the particular version that they used, and this is still talking about spheres here, the closure was not everything it needed to be, because it looks like it was ending its improvement in the series at 7. And what we saw here is we really need to keep improving. Even at the 4th level, it looks like this 4th order is probably maybe better than his 7th order. So, and that comes out of the closure not needing some improvement. Okay, every lecture I try to give you a little more stat thermo. And so let's go back to where we left off with the radial distribution function. And what we see is what we had before was the version of the canonical result for G sub n for the pair correlation function. And in order to get the grand canonical, what we have to do is multiply by this probability function for each value of n and sum all of that up. So if you haven't seen that, you'll see it next semester, I think is what Fred was hinting at. And so just to carry forward with that, then what we see is that if we take the derivative of this xi function with respect to z, which what is that? So the z is this weighting function that has to do with the chemical potential. That's what this probability function comes out to be proportional to. It has this z quantity in it. And so the little z, when you take the derivative, you get an n in front of this. And if you think about that, it has this form of n times the probability, which is the average value of n. It's related to that. And so now we have an expression for this average value of n, and I think you might be able to see where I'm heading, is that we can do a similar thing and get n squared minus n, which is a very important quantity for us in looking at the perturbation contributions, the higher order ones especially. And so this is going to be very interesting for us. Another thing is that it's this n squared minus n over the average value of n, then goes as this integral of the radial distribution function. This bold-faced bar here means it's 4 pi r squared dr for a spherical molecule. One thing I want to mention here is, or emphasize here, is that if the radial distribution function decays slowly, then this integral becomes undefined, and that can be a problem. And so we need to watch out for where the radial distribution function decays slowly, and that's what you're going to see when we start to look at these radial distribution functions for chain fluids. Well, if we continue along those lines and we do a little bit of classical thermodynamics, then we find out that this n squared minus n squared part is proportional to just the compressibility, and so this compressibility then is proportional to this integral, and that is given at that's what we call the compressibility equation. So this is a third route from the nanoscale to the macro scale. So now we have the energy equation, we have the compressibility equation, and we have the pressure equation. Problem with the pressure equation is it doesn't work if the molecule's not spherical. And since we're moving on to polymer molecules, the only ones that are really going to be useful to us are the energy, which is really easy. It's just the sum of all the site-site interaction energies. And so that's very easy to extend for a polymer. And the compressibility equation, we haven't made any assumptions. We haven't even made assumptions about pairwise additivity here. So the compressibility equation will absolutely apply to the polymers. Just one more note in passing. You've probably heard of this compressibility approximation of Barker-Henderson. And so noting how this n squared minus n squared looks is basically where I think this is actually the macroscopic compressibility approximation of Barker and Henderson. So if you understand this equation, then you can understand this equation a lot better. So now let's talk about something that's not a sphere, finally. How many minutes are we in here? 20 minutes in. Finally got to the point. All right, so where we left off last week was we said for non-spheres, we can make a slight adjustment to our Ornstein-Zernike relation. And instead of just saying H equals C plus rho HC, we can throw in this intramolecular correlation function. And this is essentially what Chandler added. And so it's a very simple extension. It's a little bit too simple, in fact. There are reasons. So the idea is that we want to incorporate this intramolecular distribution function. And one version of that would be just that, let's say ethane, there's a fixed bond length. And so that's your intramolecular distribution function. That's the beginning and the end of it. If you do a sine transform of that, then you just get sine KL over KL. And so it's just a very, very simple function to solve for that, for ethane in the RISM theory. And that was really the genesis of this RISM theory, because if you think about it, ethane is just one site type. And so now, just by throwing in the intramolecular distribution function, you're able to solve for one site type. So almost exactly the same mechanics of solving the problem, but now instead of solving for methane, you're solving for ethane. So the first step into this multi-site model is pretty simple. Second step's also pretty simple, was benzene. Okay, benzene's a cycle. All the sites are the same. You just solve for one distribution function and you're done. So let's take a look then at what happens. And so this is a very tiny graph here that hopefully we'll get across the idea. And what I want to talk to you about is this soccer goal analogy. So a soccer goal is 3 meters wide. And so if we were to post the goalie 3 meters away from the goal, there would be a lot of goals scored, right? And so think of a goal as when an external molecule makes contact with our central site. I should have said site. When an intermolecular site makes contact with our site of interest, that's a score on goal. So let me say that again. The opposing team is shooting at our goal. And our team is composed of, in the case of n equals 1, it's a goal. Okay, there's only a goal. And so whenever they shoot, they score. So they get a lot of shots on goal. I mean, they're shooting from all over. And so the probability that they hit the goal is not 100% every time, but it's pretty high. All right. But if we put a goalie in front of the goal, and let's say that we put him 3 meters away, so that's this pink curve, then the goalie stops a lot of the goals shots. And so the amount of shots that score and make contact with the goal is greatly reduced. But what would happen if we moved the goalie half the distance towards the goal? Well, he would block more goals. He would do a much better job. And more goals would hit him. And so that density, the things that make contact with him, that would go up. Yeah, okay. That's a good thing, because if they make contact with him, they don't make contact with the goal. And so that is like shortening the bond length. And so in both of these two cases, the pink one and the dotted one, N is we've got a goal and we've got the goalie. There's two bodies on our team. And so we can see we're comparing apples to apples pretty much, and we're just changing that bond length. So that's the effect of changing the bond length. If we want to study the effect of changing the number of players on our team, okay, so that's the intramolecular contribution, is when we have not just the goalie and the goal, but we have some other defenders running around the field. Then what we see is as we add more people to our team, the number of scores goes down and down and down. And eventually, if you have a real polymer, then you can create what's called a correlation hole. And what's interesting about that is, where is the energy greatest for this site-site interaction? Well, it's all the energy is here. But if you have a correlation hole so that there's no molecules actually in the region where there's energy, then the energy is greatly reduced. And so this correlation hole effect has always been kind of interesting to me, because it, again, leads to a result that seems counterintuitive. You think as you add more sites, you're going to get more energy, but because of the correlation hole, on the average, the amount of energy you get is not as much as you think it's going to be. So there's some problems, though, with using this PRISM theory. You've got to get the closure right, and a priori, you don't really know how to do that. And so you've got to go through some kind of a trial and error process. And what are you going to compare to? You've got to have some simulation results. And so this is why I got away from PRISM for a while, is I didn't have enough simulation results to compare to. Well, 20 years later, now we do. And so it's relatively complicated. You've got to know about Fourier transforms and convolutions. Hey, but we talked about that last week. Everybody knows that now, right? So that's not a problem anymore. Another problem is it's difficult to converge. And this goes back to the point I was making about the compressibility equation, that if the correlations in G get longer and longer range, then does that integral converge anymore? Or you have to go out to some really monstrous range in order to get your correlation functions to converge. And so that is something we can't avoid. Historically, it hasn't always been great relative to the simulation results, but time will solve that problem, right? we'll steadily make better closure approximations and get more comparisons, and we can iterate to improve that problem. There's a problem you can't fix with PRISM, and that is that this simple form that we're talking about here interjects some cluster diagrams in the cluster expansion. They're not actually real. And that's because of the simple form that is here. So it's a kind of a trade-off. If you want a really simple definition of your direct correlation function that PRISM uses, then the price you pay is that you interject some cluster diagrams that aren't real. And you ignore a bunch of cluster diagrams that are real, and you hope that they cancel out. So that's kind of inside baseball. That may be too much detail, but I will mention, because everybody loves Wertheim, including me, it's more than everybody, that Wertheim actually did solve this problem. If you read the fine print on the papers that he wrote in JSAT Phys, there's an integral equation theory in there. And it solves this problem, but only for the tangent sphere problem. Let's see, I need to do that. Well, okay. So these are the problems, but we can resolve some of those problems with the coupling parameter expansion, because we solve each one of these contributions, A1, A2, A3, A4, once. And so it doesn't have to converge a bunch of times. You just have to converge it once. And then you will have your perturbation contributions. Do that once for each density, put them in a bank, and now you've got your complete equation of state for that particular polymer molecule that you can apply over and over again whatever temperature, whatever density you have. And so, yeah, you still have convergence problems, but when you're applying it as an engineer, you don't care about that. You solve it once, and then you've got those. So each A1, A2 has a separate set of equations to solve. So the derivatives that you take lead to a series of equations to solve for A1, a different series of equations to solve for A2. And so we can use different convergence strategies for different orders. So this coupling parameter expansion, which I became aware of in around 2015, really is interesting because it opens up the possibility of solving this problem number 3 that I just gave up on long ago. There's a whole literature here that goes to do with the PRISM theory. It kind of comes and goes in terms of its interest level. If you just do a Google Scholar search with this keyword, Schweitzer published so many papers, it's hard to keep track. But if you look at John Curro, it's a little easier to catch up. And one that just came out was with Chao-Chun Chen and Rajesh Khare at Texas Tech. Well, C.C. Chen is of Aspen fame. So this is a very, very practical chemical engineering mainstream perspective that PRISM theory is starting to come into, all right? And so it's something to be aware of, that as time goes on, this theory will become more and more practical. And so I'll just give you a brief personal historical perspective. You can see that long ago, I was very interested in PRISM theory, got frustrated with the convergence issues until I came back quite a few years later. So let's take a look at some of the things that we learned long ago. And so this is back from 1992. And to give you an idea of why I was so concerned about convergence. So what I'm looking at here is make a plot of the site-site distribution function for pentane, okay? And let's do it with just the WCA interaction, and we see that we get just the repulsion part here. Then we'll do the simulation over again with the full potential, and we'll make a plot of that difference, of those two different radial distribution functions. So these are purely simulation results. And what we see is that this delta G, which I told you very early on, is very important when you go to A2 and higher order contributions. That delta G is getting really, really large. How large? Well, let's go over here and look at what it is in the low density limit for methane versus pentane. You see, that's a very big difference. And so whereas the methane has pretty much tailed off somewhere around 2.5 sigma, the pentane is still quite large out here to maybe 3 and 4 sigma, and that's just pentane. What happens when we go to decane, dodecane, C80? Okay, so these things are, it just looks like this cooperative attraction effect is what we called it, is becoming so large that if you want to study what's going on at all densities for a complete equation of state, then that's going to be very difficult. And another problem is that the PRISM theory actually overestimates the effect. And so the simulation result for delta G is the dots, and the PRISM theory, with the closure relationship that we were dealing with at that time, which is very close to a mean spherical approximation, overestimates that effect. And so what's happening here? Why is there this effect of cooperative attraction? Well, if you think about the goalies, imagine that it was boys against the girls, all right? And it turns out that the main striker on the opposing team, the girls have the ball, and the goalie on the boys team, they happen to be dating, okay? And so all of a sudden, there's this attraction between them, and maybe he's not going to defend quite as aggressively as he should, and so then that develops an attraction, and then the best friend of the striker, well, she's watching what's going on. She knows they're dating, and so she follows the striker. So the attraction that the goalie feels for the striker pulls in a little bit, but the best friend of the striker is following the striker. So you get two for the price of one who run in there, so that if the main striker says, "Oh, I know you're just making it easy for me because we're dating," and so she just sort of tails off at the end, her friend comes behind her and says, "I'm not dating him." She kicks the ball in the goal anyway. So there's no hope for that goalie. And so this is sort of what's happening. It's a cooperative attraction. When the goalie attracts one thing, he doesn't just attract one molecule because it's attached to other sites that are attached to that one. And so it pulls the second one in, and you have this cooperative attraction effect. And so at low density, you can really feel that effect. And it's just, why not? They all just pile on. At higher density, things get confused, and the cooperative attraction effect is way overweighed by the packing effect of just trying to put as many sites in as dense a space as you can. And things are just so muddled up that there is no cooperative attraction in that and it's just really the repulsive forces that are dominating the structure of the fluid at that point. So the main thing that is a big problem here is this long tail. And so this one seems pretty small at about R over sigma equals 4, but the PRISM estimate of that is 4 or 5 times that. And so who knows how far you have to go to get this quantity to converge, this integral. And so that's a big problem there. That cooperative attraction effect is a big problem for convergence. So now let's talk about how we can use the coupling parameter expansion then and characterize this stiffness. So there's a readily available intramolecular correlation function here. I told you that the Fourier sine transform of a Dirac delta function, which is, it says that the bond length is a fixed amount from the center of the site of interest, then a Dirac delta function, we talked about how that is going to have the sifting property, and the only thing you're going to get out of the sine transform then is the sine of KL over KL. So this is that fixed bond length contribution, and then this contribution is taking into account what's happening for the next bond over and the next bond over and the next bond over. And so by treating these A's and B's and C's as parameters and recognizing how they're related to the radius of gyration and the moments of that radius of gyration, we can characterize this stiffness, all of these A, B, C, and D parameters in terms of just one parameter, which is this xi parameter. And so this is our persistence length. So if it was a flexible chain, that would just be equal to the bond length. In other words, the diameter of one site for a necklace chain. So the counterintuitive part is that as you shorten the bond length to make something more like an n-alkane chain, the persistence length gets longer. And so that's going to be the key impact on our polymers as we go to longer and longer chain lengths. So the original CPE theory was developed for spheres. And like I said, they were able to take it out to A7. And they developed it for both square well spheres and for Lennard-Jones spheres. And essentially, it just recognizes that we can express this direct correlation function as a Taylor series in the coupling parameter. And when the coupling parameter goes to 1, we recover the potential function that we started with. And so each one of these is going to have a multiplier in beta. And so we'll be able to equate orders of temperature to orders of these A2, A3, A4. In order to apply the same approach to prism theory, we just have to take the Ornstein-Zernike equation with these omegas. We're assuming that the omega is a known function in the sense that for any given value, we can solve this set of equations for any given value of the persistence length, and then we'll pick the value of persistence length that fits our simulation data the best. The problem we ran into was that if that's all there was, that would be the mean spherical approximation. When we tried that, we didn't get good results. And so we found that we had to add this tail correction that we talked about last week to improve the consistency of the output results for the energy equation and the compressibility equation. So then we get our Helmholtz energy as we usually expect to see in terms of these derivatives with respect to the coupling parameter, and we can have a rigorous result then for how A2 is related to the outcome of this integral equation. So we've talked about the step potentials before. Here's the rainbow curve that I told you we would see when we see the A1 divided by the number of carbons. So this result here, the purple one, is for C8. And you see the difference between C40 and C80 is barely distinguishable. And so by the time we get to C80, this is just one curve. And a very similar thing happens for A0, okay? Except that we're going from a high point here to a low point there. And so it's a different rainbow, but we still get an asymptote in the long chain limit. And so this is our polymer limit, where it becomes a single curve, a single asymptote. Here is the closure that we developed. Ramana, I hate it when it does that. Ramana worked for about a year trying to figure out this correlation. He would get frustrated, give up on it for a while, and he'd send me an email and I'd write him back and I'd say, try again. And a month later, I'd get another email and eventually he figured something out. that would work. So this is not an easy thing to come up with to make your energy equation and your compressibility equation be self-consistent. But it basically, when I say the energy equation, what I'm trying to equate is the A1 term, because that's where G naught comes into play. So we want to get the A1 term and the A naught term to fit the simulation results, and that this represents that fit. So that's fine. And the persistence length, I guess I should mention, here's the A1 plot again from the previous slide. And what you could see is that when we change the persistence length from 1 to 10, A1 hardly changes at all. So it's not very interesting, the persistence length and its role on A naught or A1. But when we get to A2, oh my goodness, it makes a huge difference. And so there's something about the way the persistence length affects the fluctuations in this polymer theory and the delta G, right? And so that's where the persistence length really has a big impact. And we also did the same analysis with A3, and you see that it has an even bigger impact. So we've got to get the persistence length right in order to get all the thermodynamics for the longer chain right. But the good news is we have a lot of simulation results for A2, so we can just pick a value for the persistence length that fits the A2 pretty well and hope for the best when we make the extrapolation to A3 and A4. And so now this is the result of correlating all the data that we have for the speed MD simulations out to C80 for both the A2 and the A1. And you see, maybe not perfectly quantitative, but it's pretty good. And we'll be able to understand the physics and the trends of things that are happening when we look at this analysis. So turn the crank and calculate the A3 and the A4 contributions and take their ratios. Do they look like they're Gaussian? Nah. Well, for A3, it's not too bad. For A4, we're getting some kind of weird shoulder out here in the exact result. But remember, the higher density things, really, those fluctuations should not be as great. And we also know that the delta effect is getting smaller, and for logical reasons, because of the packing effects. So maybe it's not a bad approximation to ignore this artifact that's coming out of the integral equation solution. You see that it's still here when we get to octadecane, C80, I mean, but it's getting smaller. And so in terms of looking at the trends and wanting it to be a Gaussian, I see a Gaussian here, but I have to admit, maybe that's not the most scientific approach here. But it does give us some idea of what's the magnitude of the A2 and the A3 and the A4 at C8. And here's an interesting thing. When we think about just that ratio at C80, this one peaks out at about 165. This one peaks out at about 180. Those things are not that different. So the ratio as we go up in chain length isn't changing that much. And so that's very good to know. From that, we can then calculate all of our binodals. And we see, I plotted this upside down for a reason, but this is just your binodal curves. And what we see is we go to longer chains, then the critical temperature is getting larger, but it's not going to infinity. That's one thing. And so it's approaching some kind of a finite number. In other words, the difference between C40 and C80 is not as great as the difference between C8 and C10. There's a 2-carbon difference and a 40-carbon difference. So a 40-carbon difference isn't making much of a difference up here. And so this rainbow is kind of converging. So it looks like we're heading to some sort of finite temperature limit for our infinite chain critical temperature. And the curve is getting flatter and shallower. So the beta exponent is becoming more pronounced over a narrower range of temperatures. And what is it that determines the cutoff here? Well, when your vapor pressure goes below 10 to the minus fourth MPAs, I don't calculate it anymore because I don't feel that it's accurate. And so why this is becoming shallower is because the reduced temperature at which that vapor pressure goes to zero effectively is not as low a reduced temperature anymore. And so that's the basis for these cutoffs here. So hopefully, if you have some more questions about what this is, we can talk about those in the Q&A. Well, what does the future look like then for the PRISM theory? We said we had a question last week. How would we do this if we had polypropylene instead of polyethylene? Well, you would have to recognize that in polypropylene, you have a branch site and you have a CH3, a pendant CH3 on the chain, and then you have your CH2 sites all along. And so you've got three site types in there. Each one of those is going to have a binary correlation, intramolecular correlation. And so you've got to build up a matrix of all of those quantities. And so this is what the PRISM theory looks like for a multi-site type of molecule. It's also what it looks like for a intermolecular mixture. And so in notational form, this is the PRISM theory for mixtures is easy. There it is, done. Solving all of those various correlations and all of their interactions with each other, boy, that's a lot of work. And so that gets back to being a little more complicated. But again, it might be slightly inaccurate, but it's very precise. And that's going to be essential because we need to look at variations in how the delta G, if we want to look at how A2 is varying as a function of composition, we need to look at how the delta G is varying. And here we're doing it for two different compositions, mostly pentane versus very little pentane, mixed with methane at one density. I forgot to write the density here. I think it's like 0.44 grams per centimeter cubed. And so we can look at variations in the concentration. And we can also look at, by using the matrix form, variations for the middle site on the molecule versus the end site on the pentane versus the one between the end and the middle, the intermediate one. And what we see is that the simulations indicate that there's a pretty big change in the way that delta G looks, but the integral equation theory is not picking up what the simulations are showing us. So we need to work on that. We need to improve our closure. We need to understand better how the integral equation theory is working. And so more comparisons, more simulations. And we see a similar thing when we look at the interactions between the sphere and the different sites on the pentane molecule as a function of composition. And so this might not sound like the future because this is 1993. So if we were able to do this in 1993, it's going to be a lot more that can be done today. And so I'll leave you with that. Let's see how we're doing. 52 minutes, still a little bit over. I wanted to sort of plant the seed that this horrible looking tree is what I was trying to draw. If you were to imagine the first proto-human encountering the first proto-banana, then it might go something like this. He has this experience of biting into the banana, and he says it tastes pretty good, but it's squishy on the inside and it's kind of tough on the outside. So he comes up with a theory. He says, maybe if I peel this banana, I can just get the inside part, And he does the experiment and he says, yes, that's what I'll do. And ever since then, we've been peeling our bananas. And so this is the cycle of experience, theory, and experiment. And I don't think the monkey did or the proto-human did the simulation. So that this is sort of a more highly evolved branch is when we get to the simulation. So of all the theories, when you say theory, what do you mean? Do you mean the virial equation theory? Do you mean the Swanson perturbation theory, Wertheim's perturbation theory, PRISM theory now, density functional theory, self-consistent field theory like Cosmo? So many theories. Well, the integral equation theory, in my perspective, sits somewhere around here. All of these, PRISM theory, Wertheim's theory, they all have this cluster diagram expansion and the radial distribution function underneath them. And so you can have better and better approximations of your closure relation and incorporate more and more accuracy into those cluster diagram representations. But they're all part of this integral equation theory. And as you refine the integral equation theory, you get different branches down here in the roots. So integral equation theory deserves a little more respect than to be totally ignored. And I think it has some promise for practical applications. And so don't forget about it. I think especially when we go to study mixtures, it's going to be more and more valuable. And I'll leave it at that and open it for questions.
Thank you so much, Professor. We are now open for questions. If you want to ask one, please enable your microphone or write it out in the chat and we will read it. Yuri will be handling the questions from now on.
Okay, so who wants to be the first?
I can be the first. Very nice, Richard. I think it's well, the model that be self-consistent with compressibility and free energy. It's very interesting and not easy to find a model for that. I wonder if the artifact that you found in free energy relation fluctuations, sequential fluctuation, yeah, this one, is related with the empirical expression for past tense model, or is something more fundamental on it?
Yeah, I guess I haven't figured that out yet. As best I can say. It just surprises me that this thing is here. You know what? My guess at this moment would be that it might be an artifact of PRISM, because, like I was saying, PRISM includes some artificial intramolecular diagrams, and so my first inclination, if I wanted to get rid of this, is I would try studying this with a slightly different version than PRISM. It's called PROSA, and it was developed by George Stell and Peter Cummings over the years, and it starts from Wertheim's integral equation theory for the tangent spheres, and it generalizes that in a way that does not introduce the artificial cluster diagrams. Unfortunately, that you never get nothing for free, and so you also the theory becomes more complicated and harder to implement and harder to converge. But I think that I would want to try that. I think this might be coming from some problem like that.
So it's not related with the empirical expression that you have to come out for persistence length.
I don't think so. Yeah, because
the persistence length is going to be more important in high density.
Oh, okay. So okay, the semi-flexible chain approximation. That's where you think it's coming from. It does vary with chain length. So what does that tell us? Yeah, the persistence length. Okay, but that's a function of density. Again, packing at high density is really the strongest effect. So and it's not the. At first, I thought you were asking, could it be the Yukawa closure?
No.
I don't think it's that, because that's a very short range effect. And so at very high densities, why should this extra curve be here, especially for octane and not so much for octacantane?
Well, for the second one, for octane, for 80, is this? We have something maybe at higher density. Maybe I don't know.
It's much.
It's smaller,
small.
but smaller
Yeah.
than yeah, but smaller. Yeah. Well, let's move on.
Okay.
I still puzzle about the Gaussian expansion, how it corrects the critical point without use any kind of renormalization, or it's puzzle me. It still puzzle me. Well, I don't know. I learned from physicists that we should do some kind of renormalization to get it correct a critical coefficient, so critical let's say critical behavior, and you do this kind of expansion, suppose that it's Gaussian, and it kind of correct without exactly any kind of renormalization? Or do you think that you doing this, you get some of renormalization that you need? That's what I puzzle.
Okay, so let's think about this from a really grungy engineering perspective. Okay, so let's talk about that first. So we know that the people who develop empirical equations of state for high precision, people like Wagner, Benedict Webb Rubin, these highly parameterized multi-parameter equations of state. What do they do to get that kind of accuracy around the critical point? Well, they add Gaussians. And so if you think about what the key term in the Benedict Webb Rubin expansion is it's a Gaussian. It's something to exponential of negative density squared. And so we know that can improve things. So they never had a physical explanation for why they were adding those terms. They just knew from an engineering, just make it fit kind of perspective that helps. Well, now, why would it do that, and why should it be? Why should it have a peak here at the critical density? What does that do? From an engineering perspective, again, what it does is, remember, we're taking the derivative of the free energy, of the Helmholtz energy, to get the compressibility factor. So the derivative of this function that's reaching a maximum here is pretty much zero. And so the impact here on the pressure, or the Z factor, is zero. But we're making it sharper. The slope here is very high. So just away from the critical density, there's a big impact on Z. But right at the critical density, no impact on Z. And so when we go to look at this graph here, the steepness of the Z factor, okay, is getting higher and higher until we get to the critical temperature and it says, don't change it at all. Then it gets higher and higher in the opposite direction. So that's sort of my perspective on how the mechanics of how this Gaussian function is impacting the free energy in the range of the critical point. So that those are just sort of grungy engineering perspectives on how can this possibly happen. One other thing I would make the point of is that in this 2015 paper for square well spheres, we found some basis for rationalizing that we could make an expansion beyond, if we approximate the fourth order contribution as this ratio of A4 over A3, and then we just say that that ratio, maybe it continues for A5, A6, A7, then we can get a closed form solution to infinite order. And then that's basically what we plotted in this green curve here. So it is a renormalization in this sense. It's an exponential renormalization instead of a renormalization group renormalization. And like we say, okay, we know that can't work all the way to the critical point, but it can get us a lot closer, right? So when this quantity, log base 10 of 1 minus TR, is equal to 1, so that's 90% of the critical point. When it's 2, that's 99%. So have we gotten 10% closer to the critical point, or have we gotten 10 times closer, right? Because if you're looking at it from the critical point's point of view, we're now 10 times closer if you're at the critical point looking back. And so you get to within 1% of the critical temperature, and maybe you just say, like my daughter used to, when she was learning to count, she would say 1, 2, skip a few 100. That was some rhyme she learned in school.
Thanks. Nice discussion.
Okay, so we still got some time. Any more questions? Professor Gubbins, Professor Luis, Martin, any questions? Yeah, it's a little quiet.
Yeah, I could mention one more thing. Usually Gabriel chimes in with a question, but I think he's been doing some research on the extension of this Gaussian extrapolation to mixtures. And what he finds is a pretty simple extension does a good job. And so you might think that this empirical way of fixing the critical point for pure fluids is fine, but what do you do when you get to mixtures? Well, it turns out if you just assume a sort of one fluid mixing rule for the Gaussian correction, then you get very simple and reasonable results for your phase diagrams. Essentially, what happens is the critical point of the mixture is just adjusted, shifted to be consistent with the critical point of the pure fluids, and now you just have a smooth connection from the pure component mixture of the critical locus, and the only difference is it's correct at both endpoints and presumably in the middle. So this approach can work for mixtures, and so that's one of the things that I was concerned about, and we do have some results there. So maybe that's why Gabriel's not saying anything, is he already knows that.
I think he couldn't be here today.
Oh, okay. That makes sense. Then I couldn't see all the picture.
So what do you say? Let's wrap it up.
Yep.
So everyone, let's thank Professor Richard Elliott for this great presentation. Thank you.
My pleasure. Thank you.